All right, everybody, good to see you. There's just some major thunder and lightning, unbelievable, but I think we'll survive. And now we're going to talk about overfitting and underfitting. I think we're going to survive that too. Anyway, overfitting and underfitting is one of the primary challenges for why machine learning is hard. Is how do you balance the ability to learn the concept you're trying to learn without getting confused and lost and gibberish and noise. So we're going to go through this concept today, look at it in a couple of different ways, and hopefully get you to the point where you can start including thoughts about controlling overfitting and underfitting in your model building process as you're setting up the hyperparameters in your model search process. So there you go. Let's start with a little theorem, a little bit of math, but it's really just for a concept. The theorem is called the no free lunch theorem. And what it says is that if accuracy sub G is the generalization accuracy of your learner, L. That's the accuracy of the learner on non-training samples. So on your test samples, or actually on the performance time samples. And for the rest of this slide, I call that sort of like the generalization accuracy or generalization samples as the non-training samples. And F is the set of all possible binary concepts. I don't think binary is important, but you know, there's every possible y equals f of x that you can think of that's possible in the world that you're working in. Then there's this theorem, the no free lunch theorem. And what it says is that for any learner that you have, and what this says is this is the average generalization accuracy over every possible concept. And what do you think it is? The average generalization accuracy over every possible concept. And here's a setup. You have your training data, and you build a model on the training data you have, and then you deploy it. And now the training data presumably was drawn from the concept you're trying to predict on. But we all know that, you know, there's statistics. Everything is an IID sample. So there's a probability that the training data you have is not a good representation of the concept you're trying to learn. So, you know, in a mathematical sense, you know, with this, like we want to prove a bound and we want to say, well, what is the average accuracy, generalization accuracy of any learning algorithm? Like, why are we doing this machine learning stuff? So we can generalize, must be pretty good. Turns out average generalization algorithm accuracy of any learning algorithm is 50%. 50%? What are you talking about? Remember, this is a mathematical bound. It's not exactly a practical thing, but it's a good way to start thinking about this overfitting and underfitting concept, which we are going to talk about more in this lecture. So let's think about this a little more. It's a little crazy. So now we have two learners, learner A and learner B, and we have a set of training data that we're going to try to build a model on. So fine, they both build a model, and on the training data, one of them has great accuracy. One, you might as well be guessing. Learner B did not do a good job at this concept. It doesn't matter. That's on the training data. What we want to talk about is the generalization accuracy of these models that we've learned. Now, we can go through and do all the statistical bounds, but again, this is more of a theoretical machine learning theory result that we're talking about here. So if you say, here's the samples, x1, x2, x3, x4, and here's what the prediction of learner A's model and learner's B model is on each of those samples. Now, when you're talking about the set of all possible concepts, what a concept is that it can take any X and map it to any Y. That is what the concept is. And in machine learning, we're trying to recover that concept. But you could have a particular concept that takes X1 and maps it to 1, X2 and maps it to 1, X3 and maps it to 0, X4 and maps it to 0. You could do that no matter how many features X has, what those feature values are. The underlying concept could be that. It could be, why not? In that case, you can see that your generalization accuracy would match your training set accuracy. And you'd be like, haha, that's great. And we can use statistics to figure out how likely it is for this to happen based on blah, 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 right? But there could be a different concept. There is a different concept in the universe that maps x1 to 0, x2 to 1, x3 to 0, and x4 to 1, and et cetera, et cetera, et cetera, et cetera. I mean, that exists. You could write it down. It's just a different combination of the features that happen to be in X. The process uses those and create something different. Remember, this is all like kind of in terms of the raw stuff, and your feature engineering is going to happen, and et cetera, et cetera. But in this case, the generalization accuracy for that concept for learner A is 50%. Okay. For learner A is 50%, and the generalization accuracy for learner B is 100%. It's exactly opposite what we saw there, exactly opposite what we got on our training data. It's unlikely statistically that this would happen, but it's possible. There is such a concept that could cause this to happen if you want to get pathological. And so that's kind of like the sense of there's no free lunch. And when this corollary will drive it home a little bit more, for any two learners, L1 and L2, if there exists a learning problem where learner 1 gets a higher generalization accuracy than learner 2 does, then there also exists a learning problem where learner 1 has a lower generalization accuracy than learner 2. And you could think of it just as like sort of in an adversarial sense where you pick the training data that you apply learner 1 to and learner 2 to, and you pick the training data in such a way that learner 1 will get, let's say 60% accuracy on your holdout test data, right? So then learner 1 would be better than learner 2. Now you just flip all the labels on the test data. Now just the opposite algorithm has the 60% accuracy and the other one looks worse. So in some sense, anytime there is any way that learner 1 and learner 2 differentiate what's going on in the concept and have some different opinion about a part of the concept, then the concept could be the way learner 1 learned it, or it could be the way learner 2 learned it, and either could happen theoretically. And so the way to take this home and what you should think about, and this is a little bit of like a theory thing, and there's kind of like a trick there, and it's not very practical, but the underlying point is quite valid, and that is don't expect your favorite learning algorithm to always be the best, because no matter how well you know how to use it, how much data you have, how much more powerful it seems than another learning algorithm, there is a concept where your favorite learning algorithm doesn't do as well as, a simpler learning algorithm or somebody else's favorite learning algorithm or something along those lines. And that said, like I talk about the toolkit, logistic regression, boosted trees, and neural networks as a great set of things to learn and to use, but they're not always going to be best, not for any problem that you might bump into, just for many, many problems that you might bump into in practice. And in fact, I didn't just say one, I said 3, because each of them is appropriate for different settings with different constraints. Okay, so no free lunch. The one you like the most won't always be the best. That's what you got to think of. Okay, and so why is it that one particular learning algorithm or learning setup, training approach is not always best, and certain concepts it'll be good on, certain concepts it won't be good on? And to think about this, you need to understand this concept of inductive bias. Now, inductive bias is when you set up your learning process, just by how you do feature engineering, just by which hyperparameters you try, just by what model structure you choose to use, you encode assumptions about how likely any particular concept is. So once you've decided you're going to use a linear model, you have encoded an assumption that non-linear concepts are extremely unlikely because you can't learn them, right? They just don't exist anymore. Once you've chosen to use a decision tree, you've encoded a different set of assumptions, and that becomes your inductive bias. And then that tells you what types of concepts you are better on and what types of concepts a different algorithm might be better on. So common assumptions are, like I just said, the model structure. Is it a linear model, axis aligned tree structure? Do you want to have decision trees that can split not axis aligned? You could do that. I don't know. That would be a different inductive bias. You'd need a different learning algorithm, but it's certainly doable. And another thing is that the labels of one, all the y=1 labels are kind of near other y=1 labels, and all the y=0 labels are kind of near all the other y=0 labels. And you're not in this pathological world where every other nanometer of instance space changes class label. And so that's an inductive bias we have. Every message that is a spam looks kind of like other spam messages. It's not like, it looks almost like exactly like a good one and blah, 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 blah. And there are other types of inductive bias you have. And here we talk about even just the process that we use to do our training, the fact that we take our available data and split it up to train, test, and validate, and we use the validate data to tune hyperparameters. But even more than that, we've used the our intuition about setting up, well, which hyperparameters are we even going to try? Because like I've said many times, machine learning is the art of you can't try everything. And so another way to think of your inductive bias is, well, which things do you just not try? And why do you choose not to try them? Because they typically don't work. You have experience. Somebody who's done a lot more machine learning than you gives you, here's a good range of where to look at that hyperparameter. But there's plenty of other things you could try. And if you try those other things, theoretically, there's a concept that you would do better learning that concept by using a crazy value of a hyperparameter than by using the hyperparameter that everybody would always use, or the value range that everyone would always use. Even this assumption of IID is an inductive bias. And as we've seen with time-changing concepts, it's one that is very commonly broken in practice. And then, we have this bias of, let's train, look at the data as a time stream and cut back like a few days and use the data before that to train and the data after that to set thresholds. All of that is forms of inductive bias that you're bringing to the modeling process. Finally, there's this notion of the complexity of the concept. This Occam's razor is the principle that all other things being equal, the simpler answer is much more likely to be correct than the more complicated answer. And one notion there is that, if you have a decision tree with 3 nodes that is 100% right on your training data, or you have a decision tree with 100,000 nodes that's 100% right on your training data, you're probably going to want to take the simpler one. And we'll see in a little bit how, overfitting is learning things that aren't really in the concept but happen to be in the data. And so using a more complicated decision tree would be more prone to overfitting, but we'll talk that through. But it is an inductive bias because you might know that I'm positive that there is not a simple answer to this question. So give me an answer that has at least 50,000 nodes in it, because otherwise it's just not going to be right. And regularization is a word used to talk about encoding this assumption that simpler concepts are better in the modeling process, in the optimization process, so that you actually bias yourself towards simpler models and never even search for ones that are more complicated. Okay, so here is the set F, this big F, of every possible concept in the universe that could map the features of your data to possible class labels. And after you've set up a training process and you've gone through and written your Python code and picked the model structures, here's the concepts that you might actually learn. And I think, this is not to scale, let's put it that way, but it's quite reasonable to visualize it this way, in that your learning algorithm is only learning a tiny fraction of what's possible. But that tiny fraction would tend to be practically useful. And, that's how you build up skill, is focusing on that practically useful part as quickly as possible. And that's why when you say, well, there's thousands of machine learning algorithms, but why are the ones that we talked about ones that have been used over and over and over and over? And that's because for whatever reason, they have generally useful inductive biases built into them. That is, they may not be the best for a specific task, but they work pretty darn well across a wide range of tasks. So they are the go-to tools when you come to a new domain. And the algorithms that we're talking about in this class really have pretty much exclusively stood the test of time, in that they were invented many, many years ago, decades ago, and they're still being used in variations today. So it just kind of indicates that we've explored and found the right ways to capture things that tend to happen in this universe that we happen to live in, and not kind of in any other theoretical universe that might be out there. Now, one way to think about it is that stronger algorithms, more powerful algorithms, can learn more of F. So this might be the part of the concept space of all of F that you could learn with logistic regression. You might say that there's a much bigger part of the space that you could learn with a decision tree, because you can learn most of the linear concept with piecewise approximations of a decision tree, but not all of it. And then you can learn many, many, many things that a linear model can't represent. So it can learn more of this concept space, but that extra power comes with a cost. And the cost is that you have lost out on all of this, focusing in on your learning process on a simple set of models. Now you have to do more to control the search process that you're doing when you look for models, so you don't get lost in this kind of like much larger possible set of concepts and learn a concept that is accidentally good on your training data, but not good in generalization. Okay, so that is a little bit of orientation on what we're talking about and why these problems are fundamental to machine learning. It's not just something that, hey, we're going to get a little bit clever and solve this problem of inductive bias or of having a free lunch, and we're just going to find the best learning algorithm for everything. Now we're going to talk a little bit about types of errors that your modeling process can make or your model can make. And this is statistical, very common in statistics to say that there are two types of errors. There are bias errors and there are variance errors. And bias errors are caused because the model that you have cannot represent the concept at all. It's impossible to represent it. So every error that comes because you can't represent truth, you would call a bias error. It may not be necessarily easy to measure those. There's no like pull out an error and say, well, what caused this error? But that's just conceptually. And then variance errors are errors caused because your learning algorithm overreacts to small changes in the training data. That is, your learning algorithm, but also the process of hyperparameter sweeps that you've done, learns a model that happens to model the training data, but does not generalize well to the actual concept. Now, a lot of what you try to do in machine learning is trade off bias versus variance errors so that you make as little, you use a modeling approach that is as powerful as needed to drive down the bias errors without being too powerful and starting to get sucked into a bunch of variance errors. So let's talk about this some more. And you can say the total loss of your learning process, and remember the loss is model structure, loss, search. So we're talking about that loss component. But the total loss can be said to come from the bias part of the loss, plus the variance part of the loss, plus noise, where noise is just like training data got a little bit corrupted. Somebody hand labeled it, but they hand labeled it wrong. There was a problem in logging. I mean, there's all sorts of reasons that noise come into the process. But when you're doing machine learning, you're always going to want to look at your errors and say, well, which part of this, how much of this loss that I'm observing from the current model, how many of the errors that it's making would I say are bias or would I say are variance? And then by having a sense of that in your mind, using some of the tools we're going to talk about to come up with some sense of that, you would know how to change your modeling process to do better, right? Like, we'll go through this a little bit more. Now, let's visualize this a little bit, talk about it a little bit more conceptually, like not with the math and the kind of like crazy concepts, but a little bit more visually. And let's visualize bias. And so if our goal is produce a model that matches this concept, and the concept has X1, always label your graphs. Why didn't I label it X2? I'm so sorry about that. And so, in this range, the y equals negative. In this range, it's 0. In this range, y equals positive. Now we're going to see where the problems can come from. So we have the training data from the concept, and now we're going to learn a linear model. There's our linear model. And you can see it clearly makes mistakes. It's making a mistake on this, it's making mistakes there, it's making mistakes there. And you could pretty much say that those mistakes that it's making are generically bias mistakes because that model is unable to represent that concept. Right, there they are. Bias mistakes can't represent the concept. Now, you could slightly tweak your training data, and then you would learn, if this was the training data, totally different from last time, then you would learn a linear model again, and you could learn a very different linear model. That linear model still doesn't correctly represent the problem, but it has different mistakes. In this case, the bias mistakes have moved to, this region where you don't have training data, this region where you don't have training data, this region and this region. Those are mistakes that as you try to estimate the generalization accuracy of this new linear model, you're going to find that you're making mistakes if you have enough testing data, right? And they're different, it's different. It learned the concept a different way, but it still learned it wrong. And it still learned it wrong because it's not able to represent. Okay, so that was bias, where we saw that no matter how we have the training data, a line is not going to match the concept. But variance is about the fact that every time we saw a different set, we learn the concept a different way. And so over time, you're going to learn like all sorts of different linear splits of this instance space that do the best they can on the training data that you have, but don't properly capture the concept. And variance is about how sensitive which model it learns is to small changes in the noise. If small changes let me just erase this stuff here for a second. So if small changes in training data means that you're learning the difference between that and that and that and that, then you would say that you have maybe low variance errors. But if small changes in the training data can cause your model to learn the concept drastically different, then you would say that, you're probably going to be suffering with high variance errors. And slight tweaks to the way you're using the training data could give you a very different model for no particularly good reason. So there you go, a simple visualization of them. We're going to go through a few more visualizations, but I want to take a quick aside and say that here's the loss from 0 when you're completely perfect at the training data, generalization data, to the highest possible loss that you could have. And one way to think about your loss is that the bias is just loss that's built in because you've picked a model that can't represent the concept. So your loss might go from 0 up to, let's say, 100. And you're really never going to get less loss than 100, no matter how many times, no matter how much data, no matter whatever. You don't have the right features, you don't have the right model, you have a bias for that concept. The variance errors are going to be like, as you're trying to figure out, is my bias loss 60 or 80 or 90 or 42 or 76 or whatever it is, and you're changing small things, you're doing cross-validation and learning the model on different subsets of the training data, you're going to see your loss measurements bouncing around within some region that is plus or minus the loss that's caused by your bias, where sometimes you'll happen to look a little bit better on the training data, sometimes you're going to look worse, but no matter what the case is, the loss could be thought of as broken down into these two components. And this is one of the reasons that as you're doing a bunch of training runs, as you're sweeping parameters, you can look at the outputs that you're getting and you could see, hey, do those outputs seem to be pretty smooth? When I'm tweaking a parameter, is it a very small change in loss? Or as I move from fold to fold of the cross-validation, is the loss really jumping all over the place? And this is the first step towards getting intuition of looking at all those stats that come out of your modeling process and saying aha, I have variance errors. What should I do? What should you do? What should you do? We'll get there. So here's another example to say, well, of course, we're trying to learn a sine wave here. A linear model is not going to learn it, of course, but there's plenty of other models that you could use. And here I've tried modeling it with a high order polynomial. Right? I don't know. So, but you could see that the true concept up here is plus. The true concept on this side of the sine wave is negative. I'll draw the sine wave again so it's a little easier to see. And then you learn this high order polynomial on your training data, and it wiggles all over the darn place. It's learned the concept kind of incorrectly, super incorrectly, because it thinks that this part of the instance space is minus, and this part of the instance space is minus, and this part of the instance space is plus, and this part of the instance space is plus. With a high enough order polynomial, it fits all the training data. You can fit any actual training data with something like this, but it fits it in a way that makes tons of mistakes just because of, it's just oversensitive to what's going on. So now if you get a different training set, slightly different training set, you go to your validation data, and you could see that this one, I'm pretty sure I mapped it out, so it gets every single thing wrong. A more powerful model, perfect on your training data, completely wrong on your validation data. Now this is a pathological example. You're not going to see things go this poorly. I mean, you won't, maybe you will. I don't think I ever have, but that's not good. So for a little bit of a summary, when you're doing machine learning, you're going to have this constant balance between bias errors and variance errors. Bias errors come when you underfit the concept, that is, when your model's not powerful enough. And variance errors come when you overfit the model or when you're too responsive to small changes in what's going on. All right, so to say it again, right? Overfitting happens when you fit the training data too well. When your model is so powerful that it can find a way to fit that training data, even if that has nothing to do with the underlying concept. And overfitting can occur when your features are noisy. For example, there's a feature that's completely random. It has nothing to do with your true concept, but it's a number. And eventually, if there's enough if the randomness in that feature is proportional to the number of training data, you might have the case where your model learns, hey, I'm going to only look at that feature that's random. And I'm going to, if it has random value 1, I'm going to predict 1. If it has random value 47, I'm going to predict 0, because that's what's in your training data. So then you're overfitting to that feature, which has nothing to do with the concept, completely uncorrelated to the concept that you're trying to learn. So that's one way that overfitting commonly happens. And it really requires also that your modeling process is powerful. And powerful here could be, so you could think of it as a proxy for the number of parameters that your model has, or can your model's number of parameters grow unbounded as it's processing training data, as in decision trees? Or, with neural networks, you might try to learn a neural network that has 1 billion parameters in it. And that's a lot of parameters. That's a great amount of power. It can create very complicated models, but it's also highly prone to overfit. So you're gonna have to do a lot of work to avoid overfitting when trying to learn that many parameters. And another way to think about the power and the parameters is the hyperparameters that you use that can control how much search you allow the modeling process to do. If you tend to cut off search early, then you have reduced the ability, you've reduced the opportunity for your model to overfit because you haven't allowed it to go too far. Whereas if you allow the model to just search and search and search, eventually you are going to possibly start overfitting if your model is powerful enough to overfit the data. Now, underfitting means that you have failed to learn the true concept. And you could say that these are bias errors. They're biased either in the model structure, where you're trying to learn a linear model for a complicated thing, or they could be bias errors in your modeling process where you didn't allow enough search or enough time or enough training data for your model to go ahead and figure out what you're trying to learn. So there's, bias in the model structure itself, bias in your modeling process. And when you have high bias errors, it's said that you've underfit the concept. Now, let me just read through these. You've learned too little of the true concept. And this could happen when the features don't capture what you're trying to learn at all, which means if you've done feature engineering and you've created a whole bunch of features that have nothing to do with the concept you're trying to learn, you're not going to learn the concept, right? Even no matter what, right? You've sort of thrown it out because of your choices with feature engineering. You said, I'm only using 2 features. Well, you might have a hard time learning like something that's interesting or complicated. Another is that the model type you've picked has too much bias with respect to the true concept, as in the case with this linear model here when you're trying to learn, la-di-da. And then, you could have a modeling process that doesn't allow you to get where you need to get. So even if you are learning a high order polynomial with enough constraints that could actually learn that, but you've only allowed it like 10 iterations of gradient descent, something along those lines, you may end up learning something like that. And 10 iterations of gradient descent is not enough to ever get you to where you need to be. And because of that, your modeling process is leading to underfitting. All right. So, on that last slide, I said many, many words. I had lists, lots of stuff, blah, blah, blah. I'm going to go through one of those sub-bullets in a little bit more detail, just to give you more time with this concept, to give your brain some time to stew in it and start to make these connections. Now, first of all, this is the example we've been showing. And remember, label your axes. But this is what we're doing. And so what these features do is they expose parts of the concept to your learner. Now imagine you did this differently, where you didn't have x2. All right, so you've thrown away x2, you projected everything down on this axis, and what's going to happen? Well, it's going to be harder to learn, right? You're going to have a hard time learning this concept for the data. You could see, this sign is near there. So in this range, almost everything is going to be plus, and in this range here, almost everything is going to be minus, but in this range here, it's going to just be 50-50. So you pick a sample with an x1 value in that range, and you might as well flip a coin to get the label. And so what that means is that you're not going to learn it very well because it's, the concept isn't exposed. But if you do have a powerful model that is able to learn these variations, like in this range, it's going to heavily overfit the training data because the label is really sort of uncorrelated at that point. It's like a coin flip away. So you're gonna learn a whole bunch of like splits like that if you're learning a decision tree, something along those lines. And it's just because the concept isn't there for you to get at. On the other hand, if you're really good at feature engineering and you're like, hey, X1 and X2, those are all nice, but they're not what, they don't have anything to do with the concept, but you actually know what's going on, and you add a new X3 that projects the whole thing onto another dimension where there's a very simple answer. X3 contains the answer. Great work. You've done beautiful feature engineering. And so this captures the concept, and a simple model can learn a very low bias representation of the data just by only considering X3. And a powerful model will have low variance because there's nothing for it to overfit. You know, everything over here is looking good, everything's over here is looking good. So you can be in great shape. And this is just to say that good feature engineering can get you a long way, and that modeling power, modeling process, et cetera, all the downstream stuff, I mean, they're all related. Doing poor at any spot along the line will lead you to have errors that you will see as bias errors or see as variance errors and need to correct. And you'll need to like say, well, where is this error coming from? It could come from many, many places. All right, and I'm going to do one more example. So that last one was the effects of poor feature engineering and outrageously good feature engineering. Now the effects of noise. You know, like we said before, we could learn a decision tree for this that approximates, you know, do a split there, then we do another split there, then we do another split there. And so, you know, it's saying, well, that's minus and that's positive, and then maybe we need some more splits or whatever. But okay, fine. So we have a decision tree. It's sort of learned the concept. But what if some samples have noisy labels? Now, a decision tree can learn those noisy labels. It can say, well, oh, let's cut this region off and let's, you know, do another set of splits there. You know, I guess they'd look something more like this, but you'd split those regions off, and then it would learn like a whole bunch of splits to carve this region off. And it would say, you know, everything in here is minus, everything in here is plus, everything in here is plus. And where does this noise come from? Who knows? It could be, you know, your users got confused when they were giving you a label. Or it could be you paid somebody to hand label this stuff and they got bored. Maybe they fell asleep on the keyboard. A little noise like this can lead a too powerful modeling process to really pick up on some gibberish and come up with something that has nothing to do with nothing, just because there's a little bit of noise. Now you could, just to belabor this point, a model that is not super powerful, like a linear model, really can't address this noise. It has no way to chase that noise. It, like having these samples, it might shift the plane that it learns a little bit in that direction to, you know, to minimize loss a little bit differently, but it is not going to have the same level of overfitting problem as a more powerful model that generally you would say, well, it has a lower bias, that's better. But no, it can chase this noise, it can chase this problem, and it can get itself into trouble. So just, you know, multiple examples of how this bias variance thing is going to be a trade-off. Overfitting and underfitting are, you know, they're going to both happen, and some sense of what leads to them. Okay, so what do you have to do? You have to think about your modeling process and how it's going to interact with bias or variance errors. And if you need to get rid of variance errors, you can trade off and increase your bias errors to get rid of some variance errors. And one way to do that is to move to a simpler model. For example, logistic regression versus decision trees. Another is you could have a fixed size model. That is, you could change the parameters that control your decision tree learning process so that you just can't learn a bigger model. Another is that you could do more feature selection. Throw away features, spend more time maybe in the wrapper method to find ones that really suck all the information out of the feature set that you have. And then also fixed size search. And that's a little bit of a duel with the fixed size model because sometimes the model and the search go hand in hand. But even when you're doing gradient descent or something along those lines, you can do fewer iterations of gradient descent or put other controls on the gradient descent that keeps it from going as far as fast so that you are less likely to overfit or highly fit the training data that you happen to have. Now, a more powerful modeling process is what you'd want to use if you're willing to take more variance errors in exchange for having fewer bias errors. And so if you think you're in the place where, you know, your bias is killing you, you could use a more complex model. In our previous example, it was like, you know, higher and higher order polynomials, but this could be like decision trees or boosted trees or neural networks with more neural network structure, or even adding more features. Really throw the kitchen sink in terms of features at the problem. Even a linear model can be quite powerful, as we've seen, because of, how counterintuitive high dimensional spaces are. So, open up the feature set and let more stuff in will let you chase down the bias errors. And the other is do more search, add more parameters to the model, optimize more and more and more and more and more until you really do fit that training data as well as you can. Okay, now here I'm going to show you the types of things that you're going to see, the types of data you're going to see coming out of your modeling process that you can use to make better decisions about which hyperparameters to explore and where you are in this bias variance trade-off. Now let me explain this graph for a second. On this axis, you have the accuracy of the training data and the testing data, or maybe we should say validation, whatever set you happen to be using. And on this axis, we're talking about the min to split parameter. And that means in order to add more structure to your decision tree, you need at least 100 samples to split, or 10 samples or 1 sample. These 2 points here are for 400, values of 400 and 200 to the min to split parameter. Okay, so that's just to orient you on this chart. And so what you can see is that when you're using min to split in the range of 200 to 400 or something along those lines, the accuracy on the training data and the testing or validation data is very, very similar. And that means the amount of concept you're able to learn on the training data is translating very well to your estimate of your accuracy on your testing data. And that's, in some sense, it's a good sign, but you could see that going also from 400 to 200, it seems that things are better. Now, I haven't drawn error bars here. You could draw error bars and maybe you'd say, well, it's just noise. But a lot of times when you're doing a parameter sweep, the noise on a particular point is interesting, but also the trend is very interesting. So even if you see something like this where these guys look to be within the noise of each other, go ahead and measure another parameter, another value of this hyperparameter. So let's try something a little bit further. Now I've tried 2 more. We've tried 100 and we've tried 50. Now you can see a couple interesting things now when you look at this chart. First of all, the training accuracy has continued to go up. And if you're looking at the training data alone, you might be saying, wow, this is heading in the right direction. You may have started to if you have some error bars there, this value might be high enough so that these confidence intervals no longer overlap. And you might say that, hey, with 95% confidence on the training data, using 400 as my min to split is significantly worse than using 50 as my min to split. That's perfectly great. But look at the testing data. Now there's starting to be a problem because the accuracy, the generalization accuracy on your testing data is no longer going up at the same pace with the accuracy on the training data. And so now you got to say, oh, something might be going on here. Again, these things are small. This difference is small. So if you're doing error bounds on everything, you might say I don't know. Yeah, I mean, it's not super unlikely to have a reading that's that different between the training data and the testing data. That might just be noise. Okay, whatever. We'll use the error bounds and we'll ship. Okay. But you could also test a few more points. And now we've got a gigantic problem. When we move on to min to split of 20 and to 10, you can see that the training set accuracy is going up, 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 up. Fantastic. Just using the training data, you are on your way. You're in it to win it. This SMS spam problem is going to be solved because of you. But then you test on the test data and things are getting way, 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 way worse. And this is a very clear sign that your modeling process with this particular value of the hyperparameter and whatever features you've chosen to use, however much you've exposed to the model, this is starting to overfit. You are having variance problems, you are overfitting the training data, and you are not going to generalize well. Push it one more point, and eventually with a decision tree and really no constraint on how many splits a decision tree can put into the model, you're going to get pretty darn close to 100% accuracy. Really pretty darn, there could be training examples that have all of the exact same features and randomization in the labels. So you may not get perfect, but you're going to get very close to perfect. And then you'd see in this case that the generalization accuracy is 80%, which was worse than when you had min to split of 400. So the signal you're getting from the training data would clearly say to set this parameter to 1, but when you're testing with the testing data, you're saying, well, geez, I'm starting to overfit. And in fact, the best value for you to use just by eyeballing this chart would be something more like 100. And that's the point where there is a little bit of a gap between these two, and that's fine. No, you don't need to have no gap. What you need to do when you're doing machine learning is produce the model that performs the best on the test data. Not, you don't need to produce a model that's not overfitting. You need to produce a model that trades off the problems you have with overfitting with the problems you have with underfitting. So even though you'd say like, oh, that's not perfect in terms of the overfitting sense, it's the model you would want to use. You would want to set this parameter to 100 and then start doing maybe sweeps on other parameters to see if you could somehow tease loose other sources of problems to drive things even further. Or put another way, you've gotten, this is as far as you can get with this parameter. Go come up with some other parameters, go come up with some other features, go try more things, and you probably get further than this. So when we did the decision tree lecture, we saw that there were all these different hyperparameters that you could choose to use. And now you know why you might choose to use them and which direction you would point them in. I'm not going to go through let's just say that it's empirical question. Like try the one you want, try multiple of them, do the parameter sweeps like we just saw on that previous slide, or maybe the slide's that way. I don't know which way's behind and which way's ahead. But another way to think about it is that you could say, as I allow more structure into my model, I'm increasing the risk that I'm going to overfit. And so I'd like to add a penalty to the loss. And this might, I'd like to add my inductive bias into this loss to say, like, don't learn something too complicated. Occam's razor. Remember we talked about that? And one simple way you could do it is just add this parameter to the loss. And so then you would say, like, I take the loss that my model has by looking at how well does it predict the training data, and I add in alpha times some penalty for the number of nodes in the overall tree that I've learned. And then I pick the model that, minimizes across this joint thing instead of just minimizing on this side alone. It's just another way to think of how you're injecting your inductive bias into the loss of this. And similarly, we had hyperparameters for logistic regression. There weren't quite as many of them. They were adjust the step size, control the number of iterations or the stopping criteria. And we'll talk about regularization here in a second. But, by taking larger steps, you learn more concept more quickly, but you also are sort of quantizing the space. Like you can't get all your parameters to exactly the same values because you're taking gigantic steps versus taking very small steps. It might take you a long time to get there, but you really can wedge yourself down into the real bottom of the global optimum that you're going to find. And right, like adjusting step sizes for logistic regression, I mean, there is a global optimum. So the step size determines sort of how close you can get to that roughly. In neural networks, the space of your loss surface space is much more irregular. So adjusting the step size there can have a larger effect. We'll get there. Don't need to learn too far ahead. And of course, if you have fewer iterations or coarser stopping criteria, you're not going to get as close to, you just don't have as much range to get away from the initial parameter values towards whatever that global optimum might be, assuming that global optimum might overfit. Another thing that people commonly do, which we didn't do when we looked at logistic regression, is this thing called regularization. And it's similar to what we did with decision trees, where you take the loss that you would like to talk about and then you add some extra cost. In this version of regularization, you'd say alpha times the sum of the weights that I have for all the parameters. So what does this mean? You start with weights equal to 0, and then each step of gradient descent could add or subtract to the weights. And what this is saying is that, every time we take a step away from 0, that actually increases the loss. Or I want to encode my inductive bias that those weights should be small. Now, with this set up for encoding that, it's called L1 regularization because it's the absolute value of the weights. In some sense, this has built-in feature selection because if you think about this a little bit, if there's a feature that is not helping you reduce your loss, this is going to set its weight to 0. You're going to absolutely prefer having a weight of 0 for a feature that doesn't contribute. So after running logistic regression with a L1 regularization, you could go and throw away every feature that has a 0 weight. Fine. Another thing that people often do is this version where it's the weight squared. And square L1 versus L2, the square would mean that you penalize large values more than you penalize small values. A couple nice things to do about this is that you can take the derivative here, and so you can just fold this right into your gradient descent process, and that's what I mean by analytic solution. These would be, again, hyperparameters that you would try of turn on L1 regularization with a particular alpha or L2 regularization with a particular alpha, and that would be another tool in your tool chest when you're trying to get the best tuning of a logistic regression model and trade-off bias versus variance. All right, now you want to look at even more tools in your tool chest that can allow you to make better bias variance trade-offs, or a better trade-off between overfitting and underfitting. And you'd say that data. Machine learning people always want data. Give me all the data. I need all the data. If you're not giving me the data, it's because you want us to fail, and I don't know what's wrong with you. So main reason is that more data leads to less overfitting, all things being equal, because it's less and less likely for your model to accidentally fit training data when you have a heck of a lot of training data. The other thing you could do is clean the data. And you hear like machine learning professionals, they like joke around. You go on LinkedIn or whatever and see all these data scientists posting. It's like, my job is 80% data cleaning, 25% meetings, and 5% modeling. Because when you have noise in your data that you could actually go and control, I mean, you have to go control it. You're shooting yourself in the foot. It's terrible. It's terrible. So you can spend a ton of time trying to figure out, is there noise in the data? Because if there is, it's going to lead to overfitting, because your model, if it's powerful, is going to get confused by that noise. The noise is going to happen to be correlated with the labels in your training data, and you're going to happen to learn the wrong thing. Label noise and context bugs like errors in your logging, it's terrible. You're going to have to chase a lot of that stuff if you're a professional machine learner. Learning algorithms, you're going to find the algorithm that's best aligned with your concept. If you have a representation that matches a true concept, you're going to have less overfitting, because it's just easier for your model to slot in there, hit the contour between the different class labels without having to try to like approximate it with a bunch of garbage. And put another way, like if you can hit the contour of the concept with less search because your model structure matches it, then you don't have to do more search, and you don't have to push your model to try to piecewise approximate whatever the decision boundary happens to be. More power in your model leads to less bias but more variance problems. And so as you go into like logistic regression, our parameter sweeps were pretty simple. There's not much to do, maybe some feature selection. As we get closer and closer to neural networks, you're going to have gigantic loops of trying things and trying to avoid getting the overfitting problems overwhelming your ability to use your neural network. Some models are sensitive to noise, and that'll lead to more overfitting. Like we saw, logistic regression can't be too sensitive, but decision trees can be. Feature sets, feature engineering is very important, because this is where you are telling your model, hey, here's all the things to consider. And if you tell it some things to consider that aren't correlated, you're gonna have it chase its tail, chasing these things that you've told it to consider that it really shouldn't. So in general, if you do feature engineering and add more features, you're gonna have lower bias, you're gonna have less underfitting. But if you have too many features, you're gonna have more overfitting, because no matter what, even if they're pretty darn good features, they just give you more ways for the learning algorithm to learn the concept the wrong way. It's just more opportunity for it. And particularly if there's noise in your data in any feature, and there always is, but you may want to think about it like, hey, this is a really noisy feature. I like it, but it's got a lot of noise. I have to use decision trees and I have to do a lot of search. Oh, I just can't use that feature because it's just going to distract decision trees. So this is a type of thought process that you might want to have. Search and computation, less search will generally lead to less overfitting and more underfitting. And constraining your search, conversely, you can flip it around. And so you'd want to control your optimization process. And then a great tool that you have that we've just barely scratched the surface on how to use the tool in this lecture, and you're going to get more and more of this through the assignments, and I think we'll have another lecture where I go into it in a lot more detail. But parameter sweeps are what allows you to figure out where you are in terms of overfitting and underfitting. And hopefully because of this lecture, you now have some sense of, ooh, I look at this plot, I see this type of structure, I have an idea about what to change or how to direct my hyperparameter search. And just a few notes on that is that examine the results of the parameter sweeps. Don't just try every possible parameter and be like, okay, this one had the highest accuracy, I'm going to ship it. Look at them, plot them in a couple of different ways, and ask why. Why would that be happening? Why would that structure be looking that way? Why is it when I push that parameter value higher, I start to see this change in the output, in the generalization accuracy, but when I push it lower, I see this other change? And then as you build up your intuition and your understanding of these fundamental concepts of machine learning, like bias and variance, overfitting and underfitting, statistical bounds, what is this data telling me? What are the knobs I have? What do those knobs do? That's when you're going to start to become an actually very good machine learning model builder. And a quick summary of what we covered in this lecture: bias and variance trade-off is a primary challenge in machine learning. There's no way around it. If you're doing professional machine learning and you're not thinking of bias and variance, and you're not looking at every output and asking how bias and variance is affecting that output, you're probably doing it wrong. Doesn't mean you won't be successful in, shipping models, but you're not going to ship the best models that you could ship. Simple thing to internalize: more powerful modeling is not always best, because more powerful modeling can get confused, can overfit, and can result in things that do not generalize well, and you can't really use them in practice. You've got to learn to identify over and underfitting in your hyperparameter tuning process or your modeling process. You have to look at the intermediate results and learn how to build up an intuition about, what does this mean? What should I do? And tuning parameters and interpreting outputs correctly is key to being great at machine learning. Okay, that was a lot to cover. Hopefully the lessons will start to make a little bit more sense. The parameter sweeps that you're going to do in there, keep these concepts in mind as you go. See you next time.